Theorem 4 states the following. Theorem 4 says that the dimensionality of a space equals n perpendicular. This is the notation being used. What is n perpendicular? N perpendicular is the maximum number of mutually orthogonal vectors in it. So the theorem states that the dimensionality of a space is basically given by the maximum number of mutually orthogonal vectors that we can find in that given vector space. So let us now prove this theorem. So in order to prove this, we need to see that mutually orthogonal set of vectors are definitely going to be linearly independent. So this term mutually orthogonal definitely implies that they will be linearly independent. Why so? Because they are mutually orthogonal. So we cannot take one vector from this mutually orthogonal set and write it as a linear combination of the other vectors, because they are mutually orthogonal. It is not possible to do such a thing. So this mutually orthogonal set of vectors will also be a linearly independent set of vectors. Now let us see that if we have linear combinations of orthogonal vectors adding up to 0, let us suppose that we have such a case. So let us take linear combination of these orthogonal vectors. So let us form such a linear combination. So we have n perpendicular mutually orthogonal vectors. These are 1, 2, 3, so on and so forth up to n perpendicular, and these are a1, a2, a3, so on up to an are the coefficients in the linear combination. So let us take this linear combination and set it equal to the null vector. So we have this particular linear combination, and then after we have taken this kind of a linear combination which adds up to the null vector, let us take the dot product on both sides with any one member of the mutually orthogonal set. So consider dot product. So let us take dot product, say with the first vector. So we are taking dot product with the first vector. this dot product. Now clearly right hand side is going to be equal to 0. Dot product with the null vector will always give us 0. Here this will be non-zero. If it is unit magnitude, then that will be 1. But these terms, dot product of 1 with 2 will be 0 because it is mutually orthogonal. Then dot product of 1 with 3 will also be 0, it is mutually orthogonal. So on and so forth. All these dot products are going to be 0 and only this particular one will be non-zero. So what do we get? We get A1 times a non-zero number is equal to 0. So this is non-zero. This thing over here is non-zero. What does that mean? That means that A1 equal to 0. So this was when we took inner product with the first vector What if we take the inner product with the second vector? So if we take inner product with the second vector, we will get the following. This is taking inner product with the second vector. Again, the right hand side is 0. This here is 0. This is non-zero. Because all of these vectors are mutually orthogonal. So mutually orthogonal implies that the inner product with two distinct vectors is going to be 0. So what does this give us? This gives us A3 times some non-zero number is equal to 0, which implies, sorry, not A3, A2 times some non-zero number is equal to 0, which implies A2 is equal to 0. What if we take the inner product with the third vector? Taking inner product with the third vector, so again, by taking the inner product with the third vector, we find that A3 is equal to 0. And so on, we can continue and finally take inner product with the nth vector. note that all these inner products will be 0 except the nth vector with itself. So when we take the inner product of a vector with itself, that is not going to be 0. The rest of the terms are going to be 0 because it's a mutually orthogonal set. So we obtain So what do we obtain? We obtain the trivial solution. We obtain the following. We obtain a1 equal to a2 equal to a3, so on and so forth, equal to an. All of them are 0. So we obtain the trivial solution for the linear combination that we started off with. Remember that we started off with such a linear combination, that taking the linear combination of the mutually orthogonal vectors and setting it equal to the null vector, and then by taking dot products with each of the vectors, we find that this linear combination has only the trivial solution. So this trivial solution basically justifies the statement that we had made in the beginning, that the mutually orthogonal set of vectors will also be linearly independent set of vectors. So we have proved the claim that we made in the beginning by taking this linear combination and seeing that indeed this linear combination gives us the trivial solution. So now we have that the vectors, these mutually orthogonal set of vectors, are also a linearly independent set of vectors, are also giving us linearly independent vectors. Now we can see that this n perpendicular, the number of mutually orthogonal vectors or linearly independent vectors, may be either equal to, greater than, or lesser than the dimensionality of the space. But how do we rule out the other cases? We see that it cannot be lesser than the dimensionality by the Gram-Schmidt process, because the Gram-Schmidt process would eliminate the case where n perpendicular could be less than n by the method of construction given by the Gram-Schmidt process. And from the linear independence of the mutually orthogonal or perpendicular vectors, we see that n perpendicular cannot be greater than the dimensionality. So n perpendicular has to be equal to the dimensionality. So let us write down these statements over here. We have three possible cases. So we have case 1, n perpendicular equal to n being dimensionality of space, and n perpendicular is maximum number of mutually orthogonal vectors. Case 2 can be n perpendicular is, let's say, greater than n, and case 3 can be if n perpendicular is less than n. Now we rule out these cases 2 and 3 and select only case 1. The arguments for that is as follows. So let us say consider case 2. This is ruled out, sorry, not case 2, case 3. is ruled out by Gram-Schmidt. This is because the Gram-Schmidt theorem provides us a procedure of obtaining orthonormal basis vectors. So it provides us with a set of basis vectors. Now if it provides us with a set of basis vectors, that the basis vectors cannot be less than the dimensionality of the space, because the number of basis vectors determines the dimensionality. So number of basis vectors can definitely not be less than the dimensionality. Similarly, we rule out case 2. Ruled out by the fact that mutually orthogonal vectors are linearly independent. Why so? Because by definition of the dimensionality, so definition of dimensionality says that a vector space has a dimensionality of n if it can accommodate a maximum of n linearly independent vectors. So by the definition of dimensionality, a vector space can only have a vector space of dimension n can only have a maximum of n linearly independent vectors. So definitely n perpendicular cannot be greater than n, because n perpendicular is also the number of mutually orthogonal vectors, and mutually orthogonal vectors are also linearly independent vectors. So if we have n perpendicular number of mutually orthogonal vectors, we also have n perpendicular number of linearly independent vectors, and this n perpendicular number of linearly independent vectors cannot exceed n by this definition of dimensionality. Similarly, the case 3 that we saw, this is ruled out by Gram-Schmidt. This is from the definition of basis. So basis has to equal at least, basis vectors have to at least equal the dimensionality. They cannot be less than the dimensionality, and also n perpendicular cannot be greater than the dimensionality. So we are left with only one case, that n perpendicular is equal to the dimensionality. So we finally prove the theorem saying that the dimensionality of a space would be given by the maximum number of mutually orthogonal vectors present in that space.